Okay, let's dive right into this explainer and untangle the sometimes frustrating but honestly incredibly fascinating world of network routing. If you're a networking student, you've definitely heard of BGP, the Border Gateway Protocol, right? It's literally the protocol holding the internet together. But there are two very distinct flavors of it, internal BGP and external BGP. And confusing the two, well, it's pretty much a rite of passage for almost every network engineer out there.
To really understand why this topic is so absolutely crucial, I want you to picture this. You're trying to connect a customer's remote site back to their headquarters. You decide to use BGP to control which route to prefer. Maybe you have an MPLS link and a backup IPsec tunnel. You set it all up, hit enter, but the routing protocol simply refuses to share its routes the way you'd expect. You check the configuration. You check it again. An hour goes by, and you are literally banging your head against your desk. Actually, you don't even have to imagine it, because that exact scenario happened to a Reddit user named AfromanSays, who took to a networking forum in pure frustration. This real-world cry for help perfectly captures the struggle of mixing up internal BGP with external BGP. He essentially asked the community to explain it like I'm 5. And today, that's exactly what we're going to do. We're breaking this down so clearly that you will never have to bang your head against a desk over this stuff.
So here's our roadmap to network mastery today. We'll quickly cover 1. The big routing problem, 2. The autonomous system, 3. eBGP, crossing the borders, 4. iBGP, inside the network, 5. The eBGP versus iBGP showdown, and finally, 6. Why organizations need both. All right, let's kick things off with Section 1, the big routing problem. Let's look at the exact challenge that drove our Reddit friend crazy. It's a classic enterprise edge design question you'll for sure see in your studies. You've got a customer trying to connect remote sites back to HQ. They have multiple paths, a primary MPLS line, and a backup IPsec VPN tunnel. Now, this engineer needed to use BGP to control which route to prefer. He assumed, logically, that because everything was owned by the exact same company, he should use the internal version of BGP, iBGP. But he hit a massive brick wall because the rules of how routes are passed change completely depending on which flavor you use. The kicker? Once he switched the setup to eBGP, it suddenly worked flawlessly. So, why?
To answer that, we move to Section 2, the autonomous system.
To really grasp those rules and figure out why iBGP was being so stubborn, we first have to understand the most foundational concept in internet routing, the autonomous system, or AS. Basically, an AS is just a single organization's network. Think of a specific company, a university, or your internet service provider. Each AS gets its own unique number. The entire internet is just a massive web of these autonomous systems chatting with each other. When you configure BGP, the very first question your router asks itself is, am I talking to a router inside my own autonomous system, or am I talking to a router in a different one?
With that in mind, let's look at the outside conversation first. In Section 3, eBGP, crossing the borders.
External BGP connects different autonomous systems together. And notice how freely eBGP shares information. When an eBGP router receives a route, it immediately changes the next hop IP address to its own address. It's essentially telling the neighboring network, hey, to get to this destination, just send the traffic to me, and I'll handle the rest. Crucially, it also uses something called the AS path. Every single time a route crosses from one AS to another, the router stamps its own AS number right onto the route, kind of like a passport stamp. If a router ever receives a route update that already has its own AS number stamped on it, it drops it immediately. Boom. That is eBGP's built-in, foolproof mechanism to make sure traffic doesn't just loop endlessly around the internet.
But what happens when we step back inside? That's Section 4, iBGP, inside the network.
Things get a little weird when we switch to internal BGP, which runs between routers inside the exact same autonomous system. This brings us to the first major quirk that trips up so many students. Unlike eBGP, iBGP does not change the next hop IP address when it advertises a route to an internal peer. Let's pause and think about that because it's absolutely vital. Say your edge router learns a route from the internet. When it passes that route to an internal router via iBGP, it leaves the next hop address as the internet provider's router. But your internal router is sitting there going, I have no idea how to reach that external internet IP. I'm not plugged into it. Because of this, your internal routers have to rely on a totally different internal protocol, like OSPF, to actually find that exit door. This is a brilliant little process called recursive routing. It checks the BGP table, sees the next hop, and then recursively checks the OSPF table to figure out how to physically get to that next hop.
Okay, on to the second major quirk, which is the exact problem our Reddit user faced. Remember how eBGP prevents loops using the AS path? Well, inside a single autonomous system, the AS number doesn't change, right? So that AS path loop prevention is completely useless internally. Instead, iBGP relies on a really strict rule called split horizon. This rule basically says, a route I learn from one iBGP peer, I cannot advertise to another iBGP peer. Period. Our Reddit user had 3 routers in a straight line, fully expecting the middle one to just pass the routes along. And there's the light bulb moment. Because of split horizon, that middle router kept the routes entirely to itself to prevent a loop. To fix this natively, iBGP requires a full mesh topology, meaning every single iBGP router has to have a direct, configured session with every other iBGP router on the network.
Think about what a full mesh actually looks like as a network grows, 90. Take a second and let that sink in. That is the staggering number of manual neighbor configuration commands required to build a full mesh for just 10 iBGP devices. The math is brutal. To connect 10 routers to the 9 others, it's 90 commands. If you have 50 or 100 routers, it becomes an absolute unscalable nightmare. This is a massive limitation of iBGP, which is why advanced networks eventually use clever workarounds like route reflectors. But at its core, this strict, non-forwarding behavior is the defining feature of iBGP.
Let's put them head-to-head. Section 5, the eBGP versus iBGP showdown.
If you're studying for a networking certification, I highly recommend taking a screenshot of this cheat sheet right here. It breaks everything down perfectly. Notice the default time to live. eBGP expects peers to be directly connected, just 1 hop away, while iBGP allows peers to be up to 255 hops away across your internal network. But look closely at the administrative distance. Administrative distance is essentially a router's trust rating for a protocol. Lower is better. eBGP has a very trusted distance of 20, but iBGP? It has an incredibly high untrusted distance of 200. This literally proves that fundamentally, a router trusts external BGP routes way more than internal ones. Why? Because your internal route should really be handled by dedicated internal protocols.
Which leads us to our final point, Section 6, why organizations need both.
It's a very logical question. If iBGP is so strict, requires a messy full mesh, doesn't update the next hop, and isn't even highly trusted by the router, why use it at all? Why not just use eBGP everywhere? You need both because they serve entirely different purposes. Think of your routing protocols like coworkers with very specific jobs. Protocols like OSPF or ISIS are your internal architects. They're built for fast convergence. They instantly know the subnets, the links, and how to get from the lobby to the 3rd floor. But BGP is your heavy logistics manager. It is not a replacement for OSPF. BGP is designed to handle hundreds of thousands of heavy internet routes. If you dump the entire internet routing table into OSPF, your network would crash instantly. No joke. So you use OSPF to provide the internal connectivity, ensuring your internal routers can talk, and then you lay iBGP securely on top of that. iBGP's job is purely to safely carry those heavy external internet routes across your enterprise core without forcing every internal router to calculate those massive paths. When used right, they work beautifully in tandem.
Networking isn't just about plugging in cables, right? It's about understanding the logic and the rules of the road. By mastering these distinct behaviors, knowing exactly when routes are passed, when next hops change, and why split horizon even exists, you unlock the ability to design highly resilient enterprise-grade networks. Keep these rules in your back pocket for your next design project or certification exam, and you will never have to bang your head against a desk over a missing route table again. Thanks for joining me on this explainer, and keep learning.